Welcome to the last part of this module, where we will be exploring the benefits and challenges of precision agriculture. Economic and environmental benefits. PA is considered a key solution for ensuring global food security. The growing demand for higher quality food, coupled with unsustainable agricultural practices, climate change, and urban expansion, has accelerated the loss of arable land, jeopardizing sustainability in terms of productivity and environmental impact. PA therefore highlights both economic and environmental benefits, rather than applying inputs uniformly across an entire field based on an assumed average condition. PA also enables farmers to optimize resource use, reducing costs and increasing farm productivity. Farmers rank variable rate, VR, seed application, VR fertilizer application, and automatic section control as the three most profitable precision agriculture technologies. Approximately two-thirds of adopters reported that these technologies led to at least a 5% increase in profitability. Furthermore, the adoption of digital technologies can help address the growing challenges in agriculture. These challenges include the increasing global demand for food, environmental issues such as climate change, biodiversity loss, soil degradation, and water pollution, as well as rising social pressures reflected in stricter agricultural policies. New technologies can assist farmers in optimizing input allocation, leading to reduced costs, higher outputs, and greater resource efficiency. Specifically, the use of sensors enables better farm monitoring, allowing inputs like fertilizers and pesticides to be applied more precisely based on actual farm needs, provided farmers can effectively use the data collected. PA-enabling technologies such as driver assistance systems and electronic measurement tools can also have positive social impacts. These include potential improvements in worker well-being by reducing repetitive tasks or offering driver relief, as well as the possibility of shorter working hours. Challenges in adoption and implementation. Global agriculture is confronted with the challenges of rapid population growth and increased competition in international markets. PA techniques offer a potential solution to these issues. While PA is not yet an autonomous technological field with large-scale application, it incorporates technologies from outside the agricultural sector, raising important legal and socio-ethical concerns. The challenges surrounding PA can be grouped into two main categories: those inherent to the technologies used in PA, such as drones, robots, GPS, etc., and those that arise as PA becomes a more autonomous technological field. The first category includes issues like technological control, human safety, civil liability, and privacy concerns. The second category involves challenges such as the high costs of PA equipment, financial constraints faced by farmers, limited access to credit, and farmers' familiarity with digital tools. The economic cost of transitioning production systems to new digital technologies has been widely recognized in the literature as a key barrier to the adoption of PA. Similarly, previous studies have found that having sufficient capital is the strongest predictor for adoption, including farmers' education, which is essential for developing the skills required to use these technologies effectively. Since PATS often requires specialized training, many countries are still in the early stages of establishing the necessary educational infrastructure. Technical accessibility is also a primary obstacle in precision agriculture. Limited technology, inadequate infrastructure, and a lack of technical expertise pose challenges to precision agriculture in Africa. This is particularly pertinent given the absence of interoperability standards and technical protocols that would enable seamless communication between machinery, tools, and instruments. There are also significant limitations in the exchange of data between systems, including difficulties in connecting equipment to other components of the PA infrastructure, as well as the specialized connectivity and compatibility requirements that further complicate its widespread adoption. Furthermore, PA often relies on costly, heavy machinery, which represents a substantial upfront investment for farmers. This creates a risk of farmers being locked into a single farming model or technology provider, as they may need to sell more to repay the debts incurred from purchasing expensive equipment. The high initial costs and the potential for inadequate returns on investment can be a serious barrier to adopting PA. The challenge could be further exacerbated if external costs, such as pollution or water over extraction, were to be internalized within this farming model, even if some of these costs were reduced. These all present additional challenges that need to be addressed, as it could in the longer term have implications for food security. Another significant obstacle is the availability of infrastructure, such as network coverage. Similar issues are found in most countries, where network connectivity remains insufficient. The lack of broadband infrastructure in rural areas Connectivity issues with devices, e.g., tractors with data recording computers or satellite photography devices, privacy concerns, data ownership rights in the context of big data, and the absence of standardized protocols for data exchange between systems. PATs, which rely heavily on data exchange, can generate vast amounts of information, including detailed field-specific data on planting, crop inputs, management strategies, and harvesting practices. A major legal challenge in Europe concerns the processing of this large volume of agronomic data, which is critical for farmers and farm organizations, and the use of decision-making algorithms. While it is generally accepted that farmers own the data generated on their fields, the growing volume of data about farming, including yield and input performance data, raises unresolved issues regarding data ownership and usage. Furthermore, data quality, an ongoing issue in farm management information systems, becomes even more complex with the advent of big real-time data. Intelligent processing and analysis of this big data is challenging due to the sheer volume and diversity of often unstructured data, requiring a collaborative approach between skilled data scientists and sector production experts. Additionally, farming in Europe is highly heterogeneous, further complicating these challenges. Thus, the swift digital transformation of agriculture has led to an unprecedented increase in data collection, highlighting the need for privacy protection in advanced data analytics. However, federated learning offers a promising solution by enabling collaborative model training across decentralized data sources without the need to share raw data. PA also raises questions about the interaction between humans and machines, such as the lack of independent advisory services, the push for technology adoption, the impact on food security, and the potential for PA to exacerbate employment challenges in agriculture. Another societal challenge is the consolidation of companies providing precision agricultural services. As these companies grow, the number of players in the market diminishes, which could lead to monopolies. In the short term, this concentration of data in the hands of a single large entity could leave farmers and authorities with limited negotiating power over technology and service costs. Additionally, this dependency on a few dominant companies could lead to unfair practices and jeopardize the long-term viability of farmers. There is a significant disparity between the approaches adopted by large and small farms, particularly when it comes to PA. Additionally, there is a lack of a sufficient number of independent advisors, as many farms are operated by sole owners, primarily family farmers, who also serve as the main agricultural employers. Millions of rural inhabitants depend on family farming for their livelihoods. The size of farms and the farming methods they employ are closely tied to environmental, biodiversity, and health concerns, which in turn influence the overall shape of landscapes. Combined with the diverse traditional agricultural landscapes that constitute both cultural and natural heritage, these factors present various policy challenges. Toward this end, 3 key improvements have been identified as necessary to accelerate adoption. First, technology costs need to be lowered. Second, more reliable decision-making tools are required, as farmers need clarity on when and how to use certain applications and what the expected outcomes will be. Third, the added value of the technology must be demonstrated, with tangible profits made evident. Furthermore, more research needs to be conducted in the areas of product design that can offer an affordable and accessible alternative to the costly PAT that are already available in the market. This may serve as a push for technology adoption, especially among small-medium farm holders, to enjoy potential benefits of precision agriculture. We have come to the end of this module. Thanks for staying till the end.